morning to everyone. WE8691 Embedded Systems Design, third year, 6th semester for EEE department. Unit 1, Introduction to Embedded System Design. So in this lecture, we are going to concentrate what is meant by system and what is meant by embedded system and what is the types and the basic definitions of an embedded system, what are the real-time examples of an embedded system, and what is meant by target hardware debugging, and what is meant by in-circuit emulators, and what is meant by the direct memory access, and what is the hardware units which include an embedded system, and what are the specifications of an embedded system. So these are all the concepts which we are going to see in this lecture. So I hope this lecture will be useful for you. I am going to explain with some real-time constraints. So with the examples, I hope it will not boring to you. The content which I have included in these slides, what is meant by an embedded system, what are the types of an embedded system, and what is the processor, how we can choose the processor according to the configuration of an embedded systems, and what are the hardware units, what is meant by direct memory access, and what is the target hardware debugging. So these are the contents I have included in these slides. Right. Generally, what is meant by a system? A system is a way of working, organizing, or doing one or more many tasks according to a fixed plan, program, or set of rules. So generally a system means it's a fixed set of inputs and it will process and it will give an output. So in this manner I am going to explain the system means a system is also an arrangement in which all the units assemble and work together according to the plan or program. So in real time we are seeing so many systems. It will have some set of rules or programs. If we are giving some input, in the sense it will process and it will give a output. So all the set of system means it's having set of rules and it having inputs and it will process and it will give a output. So this is a general definition of an embedded. It's a general definition of a system. Next one is the examples of a system. It's generally a watch. A time display system. It having the hardware units like hardwares, needles, battery, dial, chassis, strap. Nowadays the digital watches having the LCD display. So many parameters having in that watch. So the general rules of watch in the sense it have to work in a clockwise directions. A needle rotates every second, a needle rotates every minutes, hours, and position after 12 hours. So these are all the rules. So which I have explained in the previous slides. A system is having set of rules and inputs. It will process and it will give an output. So in this manner I am explain an example for a system. The next is washing machine. So a washing machine, it's having a set of hardware and a software. So generally a parts means it's having status display panel, switches, dials, motor, power supply, control unit, valve, sensors, and solenoid valve. So these are all the basic units of a washing machine. So washing machine rules means it's having a spinning, rinse, drying, wash over, blinking, each step display, the process stage, and in case of interruption it executes the remaining. So these are all the rules of a washing machine. So the basic definition of an embedded system in the sense it's having a combination of hardware and software to do a particular task. An embedded system is one that has computer hardware with the software embedded. One of its important component. It is dedicated computer-based system for an application or product. It may be an independent system or a part of large systems. So generally, a simple definition for an embedded system is a combination of hardware and software to do a particular task. So generally, example for an embedded system means a washing machine, a car, a satellite communications, and car. So these are all the examples of an embedded systems. So what are the components of an embedded system? So generally, a real-time examples means our embedded system. It's a washing machine or car or satellite communication, in the sense it having all the hardware components and the software components. So in this slide, I am explaining the hardware components and main application software and the real-time operating systems. So hardware, in the sense it's having processors, timers, interrupt controllers, I/O devices, memory, ports, protocols. Then next, it has main application software which may perform concurrently the series of tasks or multitask. So it has a real-time operating system. What supervisor? The application software. It sets the rules during the execution of a application program. So generally, a hardware, in the sense it's having processor, timers, interrupt controllers, memories, ports. In the sense a processor, it's a main heart of an embedded system. So timer and interrupt controllers are other peripherals which will be interconnected to the particular processor, and it will give a specific output. So the real-time operating system means nowadays the embedded system is having multitasking operations. So the simultaneous instructions or execution. Nowadays, for example, if you are using the mobile phone, in the sense we are using multitasking. We are hearing songs, we are texting in WhatsApp, and we are texting in Facebook, and messaging, phone calls. Nowadays, all the embedded system are going to multitasking. So that will be included in the real-time operating systems. So next one is the embedded system hardware. So hardware means power supply, reset, oscillator circuits, processor, timers, interrupt controllers, parallel ports, serial communication ports, program memory, data memory, input devices, interfacing, and system application specific circuits. So these are all the hardware components. So we are going to explain one by one what is the necessity of this hard embedded structural units of an embedded systems. So the embedded system hardware, first component, processor. So every embedded system is having a processor. It's called a heart of that particular processor. So there are two units, the program flow and the data path control unit and the execution unit. So the program flow and the data path control unit includes a fetch unit for fetching the instructions, and the execution unit, arithmetic logic functions, instructions, program control task, transfer instructions, interrupt, and other routines are performed by the execution unit. So there are two important units of a processor. The first one is program flow and data path control unit. The second one is execution unit. So these are the two essential units to perform one task. And the processor is considered a heart of an embedded system, means it's going to predict all the behavior of an embedded system. So in the following slides, we are going to see how to choose a processor. So set of rules are available how to choose a processor according to your configuration of an embedded systems. The next one is timers and memory and input-output interfacing driver circuit, interrupt controllers. So these are the essential units of an embedded systems. So the next one is the classifications of an embedded systems. So there are three types of classifications of embedded systems. The first one is small scale embedded system, the second one is medium scale embedded system, the third one is sophisticated embedded systems. So we can classify this embedded system by means of the configuration of the processor. Right. The first one is small scale embedded system. It's having a 8 or 16-bit microcontrollers. So it's having a little hardware and software complexity. So usually by means of embedded C, we can develop these type of small scale embedded system. the need to limit the power dissipation when the system is running continuously. So the programming tools needed to design this kind of small scale embedded system means editor, assembler and cross assembler is available to design this kind of small scale embedded systems. The next one is medium scale embedded system. It's having a 16 or 32-bit microcontrollers or a DSP or reduced instruction set computers or both hardware and software complexity. It is having some little bit hardware and software complexity. The programming tools used to design this kind of medium scale embedded system means RTOS, real-time operating systems, simulators, integrated development environment. So many integrated development environment is available. Arduino IDE, MPLAB, Mbust IDE, IAR embedded workbench. So these are all the programming tools used to develop this kind of medium scale embedded system design. The next one is sophisticated embedded system design. The name itself, it's having some hardware and software, enormous hardware and software complexity. So the constraints by the processing speed is available by their hardware units only. So the programming tools, a compiler or retargetable compiler might have been developed for this. So name itself, it's having some hardware and software complexity. We need some sophisticated real-time operating system like VxWorks, QNX. So these are all the real-time operating system needs such kind of sophisticated embedded system design. The next one is, as I said earlier, the processor in the system means a processor is the heart of an embedded system. So for an embedded system designer, knowledge of microprocessor and microcontroller is must. So if you want to do a good embedded system designer in the sense, we must know the basic fundamentals of a microprocessor and microcontrollers. So there are two such two essential units is available: control unit and execution unit. As I said earlier in the previous slide, the heart of an embedded system is called one processor, and the two essential unit is control unit and the execution unit. So the control unit which going to fetch instruction in a memory, and the execution unit implement to data transfer and conversion operations. Processor runs cycles of fetch and execution. So the processor should be in the form of multitasking. So the simultaneous instruction execution process will have to complete in the particular deadline. So the control and the execution unit will have to work in a simultaneous manner. The next one is various processors. There are the types of processor: general purpose processors, application specific system processor, and application specific instruction processor, and ASICs. So these are the various types of processors which we are designing in embedded systems. Right. So these are the important parameters how to choose a processor for an embedded system. So the first one is instruction set, the second one is operand, the third one is clock frequency, the fourth one is complex algorithms. So first one, we have to design an embedded system means the processor configuration is must. So as I said earlier in the previous slide, we have to know what are the configurations and what are the fundamentals of a microprocessor and microcontroller which you are choosing to design an embedded system. So the maximum operand is a single arithmetic or logic operations, the clock frequency of processing speed, and a complex algorithm. That processor should complete that operation between the particular deadlines only. So these are all the steps or parameters when we are considered to select one processor. The next one is, these are all the other hardware units like a power source, clock oscillators, real-time clock, and watchdog timers, memories, I/O ports, and interrupt handlers, ADC, DAC, LCD, keyboard, keypad. So when we are going to design an embedded system, these are the necessary components to design on hardware systems. Right. So watchdog timer is a timing device that resets the system of a predefined timer. So we have to test one design of an embedded system in the sense within that predefined time interval we should meet that particular deadline. So it will use to design or it will use to estimate the performance of an embedded system by means of this watchdog timer. The next one is the examples of a small scale embedded system means automatic chocolate vending machine, robotics, multitasking toys, keyboard controllers, computer mouse, remote controller of the TV, fax. So these are all the basics or small scale embedded system design. As I said earlier, it needs only a 8-bit or 16-bit microcontroller is enough to design an embedded small scale embedded system design. The next one is medium scale embedded system like computer network, router, switch, hub, gateway, like internet appliances, entertainment systems, banking, signal tracking, video games, image filtering, processing, pattern recognition. So these are all the medium scale embedded system design. The next one is sophisticated embedded system. It needs mobile smartphones, mobile computers, real-time video and audio speech multiprocessing system, security enabled system, satellite communications. Likewise, it needs some sophisticated real-time environment needs to design this kind of sophisticated embedded systems. The next one is direct memory access. So the direct memory access, in this topic, the direct memory access, it will enable the speed of that total hardware units. So in this DMA access, what is meant by DMA access? What is the block diagram? Or what are the operations is going to be done by the DMAC, that means direct memory access controller. In these slides, we are going to concentrate the direct memory access. So the direct memory access is a IO technique, provides direct access to the memory while the microprocessor is temporarily disabled. So the IO devices are connected to the system bus via special interference circuit called a DMAC. That means DMA controller. The DMA controller may have access to main memory via shared system bus having data, address and control lanes. So let me tell one information by means of a DMAC in the sense. So all the devices are connected by the processor. If we consider one laptop in the sense, it will control the whole processor, will control the mouse, keyboard and projector and other input output devices. It will control according to the three buses, that's called address bus, data bus, control bus. So address bus, the processor will define each device by an address. So data bus, it will receive the data through this data bus, and control bus, it will control all the devices of that particular devices. So in this manner, the DMAC is controller, a CPU and a DMA controller have the access to main memory via shared system bus having data, address and control lines. So the DMA transfer is also used for high speed memory to memory transfer. So the DMA data transfer block diagram. So in this manner, we are going to see the memory and DMAC controller and other peripheral devices. It will connected by means of address bus, data bus, control bus, as I said earlier in the previous slide. So the memory will allocate the microprocessor will allocate all the hardware devices by means of this address bus, data bus and control bus. So this address latch will enable address latches will define address to all the IO devices. So generally we have two signals here, the hold acknowledgement and hold signal. The next one is DMA request and DMA acknowledgement signal. So these are the four signals is very essential to understand this concept. The next one is the data transfer block. So the two signals, request and acknowledgement are data transfer. So understand there are two signals from the microprocessor, hold signal and hold acknowledgement signal. The hold signal will request, the bus request signal will be sent to the microprocessor to release the control of buses. The hold acknowledgement signal is a bus grant signal which indicates the microprocessor as indeed to release the control of buses by placing the higher impedance states. That means the hold signal will bus request signal to release the bus signal from the microprocessor, hold acknowledgement, the acknowledgement signal which is coming through the high impedance states by the processor. The next one is direct DMA request, used to request a DMA transfer for a particular DMA channel. Direct DMA acknowledgement acknowledges a channel DMA request from a device. So these are the four signals which is essential to understand the concept. So DMA request means DREQI, means the data transfer for a particular DMA channel. D acknowledgement means acknowledge a channel DMA request from a device. Right. So the DMA data transfer, IO devices asserts a DRQ signal. The DMA controller sends a hold signal to the CPU. The CPU send a hold acknowledgement to the DMA. So DMA controller give a DMA acknowledgement back to the IO devices. So generally it's like a master-slave configurations. So the DMA controller will request to the particular CPU to give a hold signal, and the hold acknowledgement signal will be received from the DMA transfer, DMA process, DMAC to data transfer operations to the particular IO devices. So let's see what are the advantages of DMA means. It will a peripheral device read or write operations to a memory without going through a CPU. Without the need of CPU, we can do the block of data transfer to the particular IO devices. It will be the advantages of DMA. The next one is the processor can be working something else while the peripherals can be a populating memory. So the next topic is target hardware debugging. So as I said earlier in the previous slide, we are going to design on embedded system means the processor selection is one of the important parameters. So we have seen lot of rules to select on processor. So what is the meaning of debugging means? After designing an embedded system, we have to estimate the performances. If you find some errors, in the sense we have to rectify by means of this target hardware debugging. So in these slides we are going to see so many hardware peripherals to test that embedded system whether it's working or it reaching the 100% successful or. So we are going to see the target hardware debugging, which involves monitor of various signals and checking the connection between the components, and the circuit continuity is checking. So these are the major essential components. So which these parameters are working, in the sense it will leads to 100% successful embedded system. So that's why the hardware debugging components or the hardware debugging process is very essential. So these are all the tools which we can help to design on embedded systems, like a magnifying glass, multimeters, digital CRO, logic analyzers, and function generators. So these are all the components which is essentially used to test on embedded systems, because the embedded system which we are designing by means of hardware and software components. So which these tools are help to test whether it having a bugs, in the sense we can identifying the bugs and we can eliminate to achieve a successful product. So the magnifying glass is a first tool for testing the debugging of an embedded system. It's like a visualization inspection tool to test whether the proper soldering or tracking damage and incorporated multiple lens. So it acts as a visualization inspection tool. So through this inspection we can find the disconnect between the hardware components and improper soldering. So likewise we can rectify that errors in that particular hardware design, and it leads to a successful product. So the multimeter is another component of a debugging device. So multimeter is used to measure the various electrical quantities. It is used for the checking circuit continuity and signal values, polarity, supply voltage. So it will available in both analog and digital version. Generally the multimeter is a very essential component of debugging tools of an embedded system, because the supply voltage is very essential. So if we are giving the supply voltage in an accurate manner, in the sense if it produces corresponding output. So the multimeter is very essential component of that hardware debugging tools. The next one is digital CRO. So the digital CRO means we can analyze all the input output signals and pins configurations, and it will detect the analyzing interference, noise, power lines, and it will both available in an analog and digital form also. So the generally a CRO means it will give a waveform analyzing. So we can predict each and every signal strength during this due to the CRO functions to give a proper output, and it will we can analyze the whole functions of an embedded system design. The next one is logic analyzers. So logic analyzers capturing the digital data and from digital circuitry. So it's having the special connectors and clips for the target board. It captures address bus, data bus, target processors. So give an exact reflection of what happens and when the former is running. So the logic analyzer means it's another form of a target hardware debugging to analyze various digital circuitry of the embedded system design. So we can predict the address bus, data bus, and various port pin functions by means of these logic analyzers. The next one is function generators. So it's also a simulating tools. It will give a waveforms and it will give a different frequencies and amplitude. For the purpose of recovered signal, it will give a periodic waveforms. By means of this periodic waveform, we can predict the functionality of an embedded system design. Okay, thank you.